Greetings to all. My name is Maikmala Jana and this is the presentation for our paper on multi-target tracking using Ramanujan Sum based DWT. Wavelets are a powerful set of tools used for computer vision. Ramanujan Sums based wavelet transform is relatively new in the field of signal processing. In our paper, the RS based DWT is implemented to tackle the problem of multi-target tracking using wavelets, which has crucial applications in many fields. I start by presenting our objective and motivation on this work in the next slide. A novel multi-target tracking algorithm which is proposed is based on Ramanujan Sum based DWT. One of the main motivations behind the present work is to apply a novel moving object segmentation and feature-based tracking algorithm to see the performance in the multi-resolution domain using RS wavelet. Also, since the Ramanujan sums are all integer valued and normalization can be performed at a later stage, the RS-based wavelet transform is less computationally extensive and hence faster. Frequency domain analysis, especially wavelet transform, gives us flexibility for a multi-scale and multi-resolution analysis of the attributes for object tracking. These methods are often unexplored. Object tracking tracks objects detected in an input video and is a crucial part in video analysis scenarios. First step is to detect object in a frame, for which we have used segmentation and installing bounding boxes through labeling. Then tracking the detected location of the object through different frames. This slide represents the theory behind the RS-based wavelet. First, ORS, orthogonal Ramanujan sum, is defined as follows in first and second equation. Then using ORS, ORPT, that is orthogonal Ramanujan periodic transform, is developed. The normalized form of ORPT has been used to form its respective wavelet matrix while analysis. By applying the Ramanujan wavelet analysis matrix B that is formed on X, where X is an image under consideration and the Y is calculated by multiplying X and B, where Y is the decomposed image, here as given. The RS-based wavelet analysis matrices are applied for a positive Q value greater than 1 on an image of size n if the n is divisible by Q. 1 average and Q square minus 1 detailed components are found, which shows better multi-resolution decimation than existing wavelets. SVD is an attractive algebraic transform because of its endless advantages such as maximum energy packing and ability to manipulate image in basis of two distinctive subspaces. It is a stable and effective method to split the system into a set of linearly independent components, each of them bearing their own energy contribution. SVD is factorization of rectangular matrix, here A, into product of three matrices as given here. U is the orthogonal matrix having columns as left singular vector. S has singular values and is diagonal covariance matrix. These are arranged in descending order. V is the transpose of orthogonal matrix having right singular vectors in rows. S specifies luminescence of an image, whereas U and V represents geometry of image. The mathematical representation is given. Now I briefly present SVD used as fusion rule in our work. To proceed, here F is the fused frame and A and B are the respective video frames. QA and QB are the weights determining the importance of each frame components as chosen. To find the weight factors QA and QB, the given formula is used, which is stated in equation 2. X and Y are the maximum value of the selected frames respectively. In order to calculate X and Y, the eigenvalues of the covariance matrix is computed taking the datasets of both frames. Since the S matrix contains those eigenvalues in decreasing order, the first value is selected as contains maximum information. Those are used to compute X and Y. This slide defines the other techniques used in our work, that is single change detection to detect the main object for tracking, Robert cross operator to detect the edges of the main subject, which is computationally less extensive, and connected component labeling to distinguish between subjects. This is the pictorial representation of our work. Now I present the methodology of our proposed algorithm. Firstly, Wavelet transform converts 3 consecutive frames into 4 subbands. Say the video frames be I minus 2, and I minus 1, where I minus 1 is considered as the present frame. SVD-based fusion approach is applied on the I minus 2 and ith frame after decomposition. Say the fused frame is F. After the computation of fused frame F, single change detection is applied by subtracting F from the current frame. Then denoising operation is applied to prevent any kind of inconsistencies. In step 4, Robert cross edge detector is applied to detect strong edges in the wavelet domain, which detects probable object boundaries. It is the simplest method which gives good gradient response to detect boundaries of the changed intensity due to motion. Finally, post-processing is done by applying morphological operations which is required to close disconnected edges. Disconnected edges may be formed due to non-ideal segmentation process. Then region-based segmentation, that is connected component labeling (CCL) is used to have a better representation of the objects in case of multiple target. In this slide, the details of the experimental data and setup is shown. The sources of data is given as well as the type of videos considered. We have used MATLAB for our experimentation. The figure shows video frames considered for experimentation along with their ground truth. This slide presents the first set of results, which include comparing the object detection in frames with different levels or divisors considered for HAR, DB4 and RS wavelet respectively. The principle for selecting the main object is to be tracked is calculated by the significant segmented area the object occupies in the frame. The matrix used are probabilistic rand index (PRI), global consistency error (GCE), and variation of information (VOI). PRI should be greater, GCE should be less, and VOI should be less for a good matching with ground truth. The results shows that RS wavelet is more efficient in moving object segmentation as shown both visually and with matrix. Here is the second set of results which shows the comparison results along with our proposed method. Our proposed method is shown in the first row and the other methods are shown in the second and third rows. Proposed algorithm shows more efficient motion segmentation which is visible as well as measured using error matrix. For fusion of 2 frames, SVD showed better result than other traditional fusion methods. In figure, bounding box shows that in each interval of 10 frames, the same object could be tracked in case of multi-target tracking, as shown here. It is also visually compared that proposed method successfully able to segment main moving objects and track it, whereas other methods presented cannot. Here is an example of tracking with proposed method on a video of aircraft propagation whose source is given. A brief analysis of the result is given in this slide, which is stated previously. To summarize everything, according to the results shown, RS wavelet is efficient enough for moving object segmentation, and our proposed method for multi-object tracking is proved to be better as shown by the comparison results both visually and through matrix. Further, if hardware implementation can be done based on proposed method, it can yield a computationally simple implementation due to integer coefficients of RS wavelets. These are the references used. Thank you.